Hello everyone. In this video, we're going to be learning a little bit more about goodness of fit in linear regression models. So we're going to be talking about R-square, which is our conventional measure of goodness of fit. R-square measures the fraction of variation in Y that is explained by the regressors that we've added in the model. Higher the value of R-square, the greater the explanatory power of the model. And by definition, that's what R-square is. But a high n of R-square does not automatically imply that there is a causal interpretation underlying that relationship. Now, what that means is if you include an x variable, maybe your R-square climbs up to a really high number, but that only tells you that the general explanatory power of the model is greater. Explanatory power in terms of the strength of linear relationship is larger, but that tells us nothing about whether that x causes y. It does not tell us about other things being equal, other things being constant, so that we're exclusively teasing out the causal effect. So we need to be careful in what kind of, whether we attach a causal interpretation to an R-square value or not. On the other hand, a low R-square value automatically does not mean that the model is useless. It means that the explanatory power of the model is lower, but that could very well be improved by maybe adding other relevant regressors to the model. And a low R-square does not mean that does not automatically preclude us from getting precise estimates of partial effects. Meaning, just because your R-square is low doesn't mean the variability of your beta hats. So that's what we mean by precision. The lower the variability of your beta hats, the better the precision. So you may still have very precise estimates of partial effects or your beta coefficients, even when your model has a low R-square. So the bottom line here is that just deciding on models based on the R-square value alone may not give us meaningful conclusions. So to give you just a simple example, if we were to look at a program where a university just hands out grants to students to buy computer equipment, and then they're interested in seeing if that grant actually has an effect on the students' college performance, their GPA. Now, if this grant rollout was done randomly, meaning any student, a student was picked at random and they got the computer equipment, then when we run a regression there, we can estimate the causal effects because it was a randomized experiment. The ceteris paribus condition will hold by definition. But that model, though you have a causal story, may have a low R-square. Why is that so? Because you've only included one regressor, whether the student got a grant or how much that grant money is. A lot of other things could be influencing college GPAs, and that could explain the low R-square value. So that's about just being a little cautious of using R-square to interpret goodness of fit or to gauge models based on their goodness of fit. Now, we're going to learn of a slightly different measure of R-square called the adjusted R-square. Now, the R-square, as you know, is given by this expression, 1 minus SSR over SST. Now, I'm going to make some slight changes to this expression to get our new measure of goodness of fit. What am I going to do? I'm going to take the numerator, SSR, and divide it by the sample size. I'm going to take SST and divide it by the sample size N. And that gives us this expression that you see here. SSR has been divided by N, same for SST. Now, what are these terms in the brackets here? SSR by N is nothing but sigma ui hat squared by N. And that is the sample analog of your population error variance. So if the population error variance were given by sigma square u, the sample analog of that is given by this particular expression. Similarly, if population variance of y is given by sigma square y, the sample analog of that is given by sigma y squared by sample size. So these two expressions in the circles here that I've highlighted are both sample analogs of population variances. But note that when you divide these expressions by n, these are biased estimates of the population variance. And we would like unbiased estimates of the population variance. And we only need to do a minor switch to get to that. instead of dividing these expressions by n, if we divide them by their respective degrees of freedom, then they become unbiased estimators of their population counterparts. That means I take SSR and instead of dividing it by n, I divide it by n minus k minus 1, which are the degrees of freedom for SSR. And SST, I divide it by n minus 1, which is the degrees of freedom for the y variable. And when I do this change to my R square expression, the resulting expression that I get is called my adjusted R square. So my adjusted R squared is just 1 minus SSR by n minus k minus 1 divided by SST by n minus 1. And the adjusted R squared is generally just written down as an R squared with a bar on top. Now, what's the use of this R bar square? Well, remember that whenever you include a regressor, any new regressor into your model, that is going to reduce the residual sum of squares. It is going to increase the explained sum of squares. A new regressor will increase the explanatory power and reduce the residual sum of squares. And when SSR falls, so naturally, when you add a regressor, your R square will go up. But this may be incentive for people to just keep adding regressors that may or may not make sense to that story. Because mathematically, more regressors will mean R square goes up. So if somebody is bent on convincing the reader that a model has high R square, they may have an incentive to just keep increasing models, increasing regressors left, right, and center. And we don't want that, right? So adjusted R square actually penalizes you for adding new regressors. How does this penalty work out? Now, suppose we have 10 regressors initially, then the degrees of freedom for SSR will be n minus 10 minus 1, which is n minus 11. Suppose I add a new regressor, so my k now becomes 11. N minus k minus 1 now becomes n minus 11 minus 1, which is n minus 12. So n minus 12 is a smaller number than n minus 11. So for example, if suppose sample size was 100, n minus 11 is going to be 89, n minus 12 is going to be 88. So when you add a regressor, your n minus k minus 1 falls. So what's happening? In the SSR by n minus k minus 1 term, your SSR is falling, n minus k minus 1 is also falling. So we don't quite know what is happening to that entity as such. And we're not going to go into the details, but this is the way in which the penalty actually works. So in fact, there's a mathematical statement or there's an algebraic proof to show us that R bar square will actually increase only when the t-stat of the newly added regressor is greater than 1 in absolute terms. Now notice that your t-stat being greater than 1 does not immediately tell us that it's a statistically significant variable. Your t-stat needs to be greater than 2 for a statistically significant variable, absolute value in that sense. So we may be adding a regressor that's not statistically significant, but it needs to have a sufficiently large t-stat in order to push up the explanatory power of the model. So as you get into more advanced programs in economics, you'll be able to unpack this story much better. But now it suffices to know that R bar square penalizes our addition of new regressors, and in this manner, it helps us take a better judgment call on which model is a better fit than the other. So so that's the formula for R bar square, and just by rewriting a few terms, you can express R bar square in different expressions, and I'll leave the algebra up to you. Now, the best use of R bar square is to it helps us choose between non-nested models. So here's an example in this slide. So we have the R&D intensity of a company being a function of the sales of the company. So the first model here has it's a level log model where your x variable enters in terms of its log value. In the second model, your dependent variable is still the same, but your x variable enters quadratically. Now, given that both the models have the same y variable, we can actually go ahead and compare the r bar square here to make a detailed, to make a careful comparison. Now, if we were to just compare the r square values, well, r square in the first one is just 0.06, the second one is 0.148, meaning 15% of the explanatory power comes from our regressors in the second case, whereas only 6% of the variation is explained by the regressor in the first case. So naturally, second one is probably better. But we have to watch out here. We can't do that comparison because the first model has fewer x variables, second model has more regressors. So instead of doing that, we can go ahead and look at the r bar square, which accounts for this addition of regressors. And if we look at that, we have the same conclusion again. R bar square in the second case is better, telling us that the second model, the second variation, explains a greater part of the variation in y. And even though you have accounted for the additional regressors, the quadratic model still does a better job. So we could use R bar square in such cases. You could also use R bar square where, suppose you have a regression of y on, say, x1 and x2. And suppose you have another regression of y on x1 and say x3. So the model has the same dependent variable, has the same number of regressors, except that one of the regressors is different in each case. In such cases as well, you can use R bar square to compare which of those regressors gives you a better fit. Quick note, you cannot compare models based on their R square or R bar square if they have different dependent variables. So in this example, the first model, the dependent variable is salary. The second model, the dependent variable is log of salary. Now, salary and log of salary are very different. We cannot use R square to compare R square or even R bar square to compare such models, primarily because the dependent variable is different. Your R square is only explaining the fraction of variation in the dependent variable. If the dependent variable itself is different, you can't go ahead and make those comparisons, right? And so that's why we need to be careful with how we do these, how we use R square and R bar square. So just to speak a little about this notion of adding variables, adding regressors into our regression model. Now, we add regressors because one, we want to get ceteris paribus stories, effects, and then we also want to improve the explanatory power of the model. Now, when we just keep adding regressors into our model, we have to keep the ceteris paribus relationship in mind at all times. And if we are unmindful, we may run into some very strange regression models that we construct. So here's an example. Suppose we are bringing in a tax on beer in the state, and we're going to look at whether the tax has an effect on reducing traffic accidents, traffic fatalities. Sensible argument, right? When you tax beer, that's going to reduce alcohol consumption. Hopefully people are driving safer, and that should reduce fatalities. So we run a regression model of this type, where the fatalities are regressed on a bunch of variables, where the tax variable is the one of interest. And then we're also accounting for the number of miles driven and a few other, the percentage of drivers who are male, percentage of drivers who are in the 16 to 21 age group, and so on. Those are all regressors which you can, which we all understand why they would affect traffic fatalities. But notice that we have not included a variable that measures beer consumption. Now, the story is that beer consumption should affect fatality rate as well, but we are very carefully not including that. And why is that so? Think of the pathway through which we are describing this effect, right? When there is a tax, if beer tax goes up, the consumption of beer will come down, and that will reduce drunk driving, so when beer tax goes up, beer consumption comes down, which further reduces your drunk driving and therefore reduces traffic fatalities. So a change in beer tax will, by definition, change beer consumption. Now, if I included beer consumption as another regressor, what's the ceteris paribus interpretation of that tax variable? Well, for a 1 unit change in tax, keeping all the other regressors, including consumption constant, beta 1 tells me the reduction in fatalities. Well, can I increase tax and expect beer consumption to remain constant? No. And in that case, the ceteris paribus story doesn't hold anymore. And for this reason, because consumption varies with taxes, we don't include that regressor in our model. And this sort of thinking about models is something that you build over a period of time with just practice. And this is the part of econometrics that I like to call as art rather than just science. I mean, it is science, but you just need to be very tactful in how you do this. Here's another example. Suppose we're looking at the relationship between use of pesticides and family health expenditures. Maybe we are talking about farmers' families. Now, in a regression where family health expenditures, so this is the Y variable, pesticide use is the X variable. So if health expenditures are regressed on pesticide use, we should be careful to not control for doctors' visits in this case. We should not, if we include pesticide use as a regressor, we should not include doctor visits. Why is that so? Because if you're looking at the relationship between, if you're looking at the marginal effect of pesticide use, right? For using 1 more kilo of pesticides in the farm, holding everything, including doctor visits, constant, what's the change in health expenditure? But if you're using more pesticides, which are harmful chemicals, those are very likely going to warrant doctor visits. So doctor visits will change when pesticide use changes. So it doesn't make sense to keep doctor visits constant while changing pesticide use. And that's what we'll be doing if we add doctor visits as a regressor. And that's the case. That's the reason for not including that as a regressor. So we should be a little careful in whether we're controlling for too many variables in our regression analysis. Which then leads us to the question, how do you do this? How do you game the system? When you add more regressors, you run into this ceteris paribus problem. You may have regressors that are related to each other. There could be a multicollinearity issue. But on the other hand, adding more regressors means lesser residual sum of squares and lesser error variance, which is good for us. So we don't know which is going to be stronger in this case. So how do you determine which regressors to add? Well, if you have identified a regressor that's not correlated with other regressors, you should go ahead and add that. And if they happen to reduce your error variance without exacerbating the multicollinearity problem, I mean, if you add in the regressor and there's no multicollinearity issue, you should go ahead and add it. So here's an example. Suppose we are estimating how a person's individual consumption of alcohol depends on the average county price of alcohol. Now, the county price is the key regressor of interest. If you think of other regressors that you can add to that equation, a lot of individual attributes of the person could be included here. Of course, whether how old is the person, their gender, where they live, all of those could explain their individual alcohol behavior. And those individual attributes are going to be unrelated to the average price of alcohol in that county. So we don't have a multicollinearity issue. And just by adding more regressors, our explanatory variation is going to get better. So, and that's a good enough that's a good enough way of figuring out how to get more regressors into the model. So I will stop this section here, and I will see you in the next video to discuss the final part of this chapter. See you there.